Hello viewers, welcome back to this channel. So in this video we're going to be finalizing transition elements. This video is presented to you by Yusuf, and you advise subscribe to the channel, share the video to your friends so that you can all benefit as a group. So in this video we are going to be covering copper together with its reactions, together with its chemistry as a transition element. And you're going to be tackling it with zinc. So this video is presenting two chemical properties of the transition elements of copper together with zinc. So now with copper, we are going to start with its extraction, as majority of the transition elements we have been covering, except nickel, cobalt, and titanium together with vanadium. They're the only transition elements that do not have extraction parts. So just like other elements, we have the chief ore together with other ores. So the main ore from which we extract copper from is called copper pyrites. So copper pyrites is presented by this formula, CuFe sulfide. And other ores from which you can extract copper, because usually when we ask for this extraction, part A Roman number 2, we are always going to ask you for other ores from which copper can also be extracted. So there are other ores that are mainly common, which are mainly present in majority of the textbooks. So one of them is going to be cuprate, which is the same as copper 1 oxide, and also copper glance. Now copper glance is the same as copper 1 sulfide. Now let's look at the extraction process using the chief ore, which is copper pyrites. So you're going to be saying that the ore is first concentrated by froth flotation. Now remember, in the previous video I told you that there is a common error while presenting this pairing. The word flotation is F-L-O-T. There is no A. Majority of you write this floating of water. It's called froth flotation without A. So this A is not there, and that's where majority of you miss marks from. So the ore is concentrated by froth flotation, in which the finely divided and powdered ore is going to be mixed with water containing a frothing agent. And after mixing your ore, which is finally powdered, with water containing the frothing agent, you are going to blow air. So we are going to say that a current of air is going to be blown through the mixture, producing a froth. And this froth, remember that the froth is always going to be at the top of the surface. So this froth is going to be containing copper bearing particles. Now, when this froth being at the top of the surface of our solution, or of the water in which you have placed it containing the frothing agent, the earthy impurities are going to be weighted. In other words, they are going to absorb the water, and after absorbing the water, they are going to sink to the bottom of the tank, whereas the froth is going to be skimmed off and dried. Remember that this froth is the one which is containing our ore. Now we have separated some of the earthy impurities from the ore, but we are remaining with the inorganic impurities that are remaining or that are intact with our chief ore. So to remove that, we are going to say that the ore is going to be first roasted in a limited supply of air to convert the ore to copper 1 sulfide together with iron oxide and sulfur dioxide. So whenever you hit iron pyrites, or whenever you hit pyrites alone, pyrites is iron sulfide alone. In oxygen, you get iron oxide together with sulfur dioxide. But if you're eating copper pyrites, where you're having also copper inclusive, you are going to get copper 1 sulfide, iron 2 oxide together with sulfur dioxide. Now, one thing you should take away from the extraction of copper is that majority of your products are going to be in the oxidation state of copper, which is +1. And the reason for that is because most of the reactions, we are going to do them in a limited supply of air or without any air. So that means that we don't oxidize copper to its most stable oxidation state, which is +2, since we limit the conditions that are present for such reactions to take place. So copper and sulfide burns in oxygen or in sufficient oxygen to give us copper and sulfide iron oxide together with sulfur dioxide gas. Now, after roasting our ore, the product of roasting or the products after the roasting are going to be then heated with silica in a closed furnace. That means when saying a closed furnace, it means in absence of air, and that's what I've been telling you. We do it in absence of air because majority of the products that you're having can undergo oxidation. You have seen that copper is not in its stable oxidation state, so we do it in absence of air, so that only the reaction of silica and iron oxide takes place. And remember that iron oxide is present as an impurity in our ore. So you're going to say that therefore iron oxide is going to react with this silica, which is the same as silicon oxide, to form iron silicate. Now this iron silicate which is being formed is going to float on top of the copper 1 sulfide being formed, and so it's going to be skimmed off. You can either be skimmed off or poured off. So iron oxide reacts with silica or silicon oxide to give us iron silicate. Balancing of the equation follows the same principles just like we discussed earlier on. I hope you understood those steps. Now, for someone who is having any concern, you present your issues. If you're having any concern, you present your issues under the comment section, and your concerns will be answered in the next video. So if you're having any issues anywhere, you put the concerns under the comment section of this video, and your answers will be presented in the next video. So going to the next step, we are going to say that the molten copper 1 sulfide, it's molten because we have heated silica and iron oxide without absence of air. So that means that our copper 1 sulfide, which was formed, undergoes melting. So the molten copper 1 sulfide is going to be heated in limited supply of oxygen or air, causing its partial oxidation. It's only partial oxidation because we are controlling the amount of air or oxygen being placed into the combustion tank. So with limited oxygen, copper 1 sulfide binds to give us copper 1 oxide, and we write that equation. So copper 1 sulfide reacts with oxygen to give us copper 1 oxide together with sulfur dioxide gas. I say that the balancing follows the same procedures like we have been handling before. So I've over-explained equation balancing in other transition videos. I hope that before you to proceed to this video, you can now write out this equation and you balance it on your own with the knowledge that I already gave in other videos. So the copper 1 oxide, after being formed, is going to be mixed with unchanged copper 1 sulfide, but this is going to be done in absence of air, and then heated strongly to form molten copper, which is our blister copper, and sulfur dioxide gas is also going to be formed eventually. Now, just as a shortcut for you to master this extraction, if you look at the procedures that you have been passing through, you have seen that you have been alternating limited air or controlled air, and then next procedure was no air or absence of air. The other one is limited, the other one is no air. So for you to master the arrangement, how this extraction is arranged, you have to use that same criteria. Understand that it goes interchanging, or it's intermittent. Limited, no absence of air. Controlled air, absence of air. Controlled air, absence of air throughout the whole procedure. So this previous step, we are presenting controlled air. By the previous one, it was absence of air. So here we have gone back to absence of air. And here we are heating copper 1 sulfide together with the formed copper 1 oxide in absence of air. And we do this so as copper 1 oxide can reduce the copper 1 sulfide to form blister copper together with sulfur dioxide as a gas. So copper 1 sulfide reacts with copper 1 oxide to give us blister copper, which is a liquid, together with sulfur dioxide gas. And we are going to say that the blister copper is then purified by electrolysis using direct current. Now with blister copper is going to be the anode, and the pure sheet of copper is going to be the cathode, and copper 2 sulfate solution is going to be our electrolyte. Now I hope you remember this experiment in O-level, where I used copper as electrodes and you are using copper 2 sulfate as your electrolyte. Obviously you are going to get copper being deposited at the cathode, and that's what is going to be your pure copper, and extraction of copper will be complete by that step. Now proceeding, let's look at what takes place when you electrolyze a solution of copper to sulfate. Now on electrolyzing a solution of copper to sulfate, now remember in electrolysis, we told you that anode means anions. So an goes with an. It means that anode discharges anions, and then cat, or which is the cathode, discharges cations. So cat, an. So cat is for cathode discharging cations. An is for anode discharging anions. So that's what you should put at the back of your mind. Now proceeding, we are going to say that. So let's look at what takes place together at the anode together with the cathode. So you're going to say that at the copper anode, remember that we are using copper, our blister copper as the anode. So we're going to say that at the copper anode, this blister copper is going to dissolve, forming copper 2 ions in solution. And to balance up this equation, we balance it up with electrons. And at the cathode, the pure copper is going to be deposited, because we said that at the cathode, cations are going to be discharged. So copper is deposited because copper is existing in high amounts. So it requires less energy for it to be discharged. And we shall look at this in details under the topic of electrochemistry, which is the next topic to be uploaded. So copper ions give us, when they're discharged, they're going to give us the copper solid, which is the copper which we are trying to extract. And our extraction complete will be done at that step. I hope you have understood that extraction process. Like reminder, I've told you, if you have any concerns or any issues, try to put them in the comment section. Some of you come to my WhatsApp, which is always clogged with a lot of messages. So try to present your issues on a specific video about the issue or area of concern you want me to tackle on. And I'll be responding within the next 2 weeks. So reactions of copper. So one of the reactions of copper, let's look at the reaction with air. Like I said, copper, the stable oxidation state, in absence of, when provided the conditions are met, its stable oxidation state is going to be +2. So like we said that before writing any statement, before giving any equation, you must give a statement, but that statement must contain conditions together with the products, names of the products being formed. So for us to write a statement before a reaction of copper with air, we are going to say that heated copper is going to react with air so that we form copper 2 oxide. So copper reacts with oxygen when heated to give us copper 2 oxide. Balancing follows the same criteria. You start balancing the metal, you go to the non-metals. So with water, now just like we said, there is no metal, copper does not react with dilute water. Copper does not react with dilute or cold water, or water at any condition. So looking at the reactions of copper with chlorine, copper reacts with chlorine when heated because chlorine is a gas. So since chlorine is a gas, it must be dry in nature. Like I said, your statement must contain conditions for the reaction to take place together with the products being formed. So you're going to say that heated copper reacts with dry chlorine gas to form copper 2 chloride. So copper as a solid reacts with chlorine gas, forming copper 2 chloride. Balancing follows the same criteria. Now with alkalis, now since copper as an element is, now let me explain this in details because majority of you seem not to understand this. Copper as an element, that means that copper in its solid state does not react with alkalis because it's a basic element. But if copper is present in test solutions, if copper is in form of ions, then their copper can react with alkalis. For example, if you add sodium hydroxide or ammonia solution to a solution containing copper ions, you are going to get observable changes according to its chemistry and the practicals. But if it's copper as a metal or as an element, it does not react with alkalis because it's a basic element. And the same explanation applies to group 2 elements. So group 2 elements or metals do not react with alkalis, but if they are present in solution as ions, then they undergo reactions with alkalis. The reason why they don't react with alkalis in their solid state or in their element form is because they are basic elements in nature or basic metals in nature. So a base cannot react with a base. Now let's go to the reactions with acids. Now we're going to first look at the reactions with dilute acids, and I'm going to say that copper does not have any reaction with dilute acids. Now the only reaction that it has, it would have been dilute nitric acid, but there nitric acid is not dilute. Nitric acid is halfly concentrated, so we call it moderately concentrated. Now let's look at the respective reactions. So we are going to, since it doesn't have any reaction with dilute acids, we are going to look at its reactions with concentrated acids. So one, copper is going to be oxidized by all oxidizing acids, and the oxidizing acids, we have hot concentrated sulfuric acid together with hot concentrated nitric acid, and we say that such reactions are redox reactions, and I gave a 10-minute video explaining how you can derive the balancing of these equations. So if you didn't watch that video, you have to go back and review it immediately. So copper is oxidized by hot concentrated sulfuric acid, copper to sulfate, and after this acid oxidizing it, the acid gets reduced to sulfur dioxide gas together with water. So copper as an element is oxidized by hot concentrated sulfuric acid, giving us copper to sulfate. And the acid, after oxidizing, it gets reduced to sulfur dioxide together with water. Like I said, I've already talked about the balancing of these equations with a 10-minute video uploaded in the inorganic chemistry playlist. So you make sure that you review that so that equation balancing gets easier for you if you are sure you didn't review it. So copper is also oxidized by concentrated nitric acid to give us copper to nitrate, and after the acid oxidizing, it gets reduced to nitrogen dioxide together with water. So copper is oxidized by nitric acid to give us copper to nitrate, and after the acid oxidizing, it gets reduced to nitrogen dioxide and water. Equation balancing is by redox reactions because we're having a reaction containing a concentrated acid together with a metal or a compound. And we say that such reactions are going to be redox reactions for as long as you're having both oxidation and you're having also reduction. Now going to the other reaction which I've talked about, reaction with moderately concentrated nitric acid. Now copper reacts with moderately concentrated nitric acid to give us copper to nitrate together with nitrogen monoxide and water. So we can either call it moderately concentrated, and other textbooks are going to call it halfly concentrated. So moderately concentrated or halfly concentrated nitric acid oxidizes copper to obtain copper to nitrate, and the acid after there gets reduced to nitrogen monoxide together with water. And the equation for that is also a redox reaction. So in this case, nitric acid is going to oxidize this copper, and we are going to form copper to nitrate. But after the acid oxidizing, it's going to form nitrogen monoxide, unlike with concentrated nitric acid where we form nitrogen dioxide. When we use the halfly concentrated, we form nitrogen monoxide, halfly concentrated or moderately concentrated, together with water as our byproduct. Now let's look at the oxidation states in which the various compounds of copper do exist. Now copper exhibits two principal oxidation states. The one is +1 and the other one is going to be +2. Now when you're introducing transition elements, we talked about how these oxidation states come about. So we're going to say that let's try to explain how each of them comes about, how copper 1 ions come about and how copper 2 ions come about. So by losing one electron from the 4s sub-energy level, I told you avoid this word orbital, though it's what I included in these notes. So from the losing one electron from the 4s energy level leads to formation of the copper 1 ion. Because the 3d orbital is going to be fully filled with electrons, that means that copper 1 does not show typical transition metal properties. Because after removing the 1 electron from the 4s energy level, you are going to leave your 3d sub-energy level or orbital to be fully filled with electrons. And once it's fully filled with electrons, that means that it's not going to show transition properties, the chemical properties that are contained by transition metals. Because we say that for transition metals, to exhibit their properties, they must have a partially filled 3D sub-energy level. So if copper 1 ion has a fully filled 3D sub-energy level, that means that it is not going to show the typical transition metal properties. So for the copper 2 ion, it's going to be formed when you lose 2 electrons, but one electron is going to be from the 4s sub-energy level, and the other one is going to be lost from the 3D sub-energy level. Now, since one electron is going to be lost from the 3D sub-energy level, it's going to leave the copper 2 ion with a partially filled 3D sub-energy level. I say that to avoid orbital. Use sub-energy level instead. So you're going to have our copper 2 ion with a partially filled 3D sub-energy level. And since elements or transition elements, for them to show their typical properties, they must have partially filled 3D energy levels. We are going to conclude and say that hence the copper 2 ion is going to show typical transition metal properties in its compounds. That means that these compounds are going to be mainly colored, and that's why you're going to find that the few copper 1 compounds that you're having, such as copper 1 iodide, which is a conformation for copper in your practicals, is going to be a white precipitate. Unlike other copper compounds, which are going to be existing in the +2 oxidation state, that are going to be colored because the 3D sub-energy level is going to be partially filled. So concluding this, you're going to see that from the electronic configuration, copper 1 is going to be expected to be more stable than the copper 2 ion. However, this is not going to be the case. So this is not going to be the case because here, remember that now here we are going to go back to thermochemistry a bit. Thermochemistry say that the stability of a compound is going to be determined by the energy values. The more negative it is, the more it's going to be. That means that the more negative it is, the more exothermic the energy is going to be evolved. And if you look at that in terms of solution, because we are dealing with ions, the negative part of enthalpy of solution is hydration energy. So that means that, and if you look at the factors that affect hydration energy, one of them is going to be ionic charge together with ionic radius. And if you take it in that explanation, you'll find that copper 2 ion is going to have the largest ionic charge together with the smallest ionic radius as compared to the copper 1. So that means that in solution, compounds of copper 2 are going to give more hydration energy, and therefore they are going to be more exothermic, hence more negative as compared to those of copper 1. So we expect copper 2 compounds to be more stable as compared to the copper 1 compounds. I hope that has been understandable. So let's go to the notes that have been written. I hope you have the best ways to understand it in terms of explanation. So we're going to say that, however, this is not the case because copper 2 is more stable than copper 1, and this is because the copper 2 ion has a higher charge density than the copper 1, thus it produces more energy upon hydration, enough to compensate for the second ionization energy, forming stronger bonds in its compounds than the copper 1 ion. Like I've told you, this is just a variation in English, but it's about explaining in terms of hydration energy that is going to be given off when both of their compounds are placed in solutions. We look at which one is going to give off more hydration energy, and the higher the hydration energy, the more negative the enthalpy of the solution gets, and the more negative the enthalpy of the solution gets, the more stable is that compound. I hope you remember that under the topic of thermochemistry that we still covered on this channel. Now let's look at some of the copper 1 compounds. Now under the copper 1 compounds, you're going to say that the copper 1 ion is very unstable in water and also undergoes disproportionation to form copper together with copper 2 ions. Remember that I talked about disproportionate reactions in details still under these videos, so I hope you remember that. So copper 1 undergoes disproportionation, and you say that disproportionation reaction is that reaction whereby we are going to have both oxidation together with reduction happening at the same time on the same species. So here we came from +1, and here we went to +2 as the oxidation state. So that's oxidation. But here the oxidation state is 0. So it means that here copper was reduced, but here copper was oxidized. So a disproportionation reaction is that reaction in which we are going to have both reduction and oxidation happening on the same species simultaneously or at the same time. Now looking at another compound, you're going to look at, or the first compound, you're going to look at copper 1 oxide. Now copper 1 oxide is a dark red solid which can be obtained as a precipitate by simply reducing copper to sulfate using reducing compounds. You can use reducing compounds such as aliphatic aldehydes in alkaline medium, and such reactions are going to be very common in organic analysis and are both practicals together with the questions that are being asked about reagents together with the observations. So when you get a solution containing copper 2 sulfate or copper 2 ions, and then you add an aldehyde present in an alkaline solution or in an alkaline medium, you are going to get these copper 2 ions reduced to give you the copper 1 oxide. So after being reduced, this is a reddish brown solid that you view as your failing solution. So the observation here is going to be formation of the reddish brown solid or precipitate, because it's the one that you'll be viewing, since others are going to be aqueous together with liquid, and they can't be under the observation because they're going to be colorless. So the other thing is going to be, the other property about copper oxide is that you're going to say that it's going to be insoluble in water, but it's going to undergo disproportionation in dilute sulfuric acid, and this is a very, very common reaction under mock bodies. So copper 1 oxide undergoes disproportionation when placed in acidic medium to give us copper 1 solid together with copper 2 ion, and later we also form water. So the observation here, because mock bodies, they are going to question you for state what is observed and also write the equation for the reaction. So the observation you see here is going to be a brown solid. Formation of a brown solid. Don't say deposit. We do not have deposit in chemistry. So formation of a brown solid, that brown solid is going to be for copper as a metal being deposited after reduction. Now since copper 1 has undergone both reduction and oxidation, we consider this to be a disproportionation reaction. And that's why we are saying that copper 1 oxide is insoluble in water but disproportionates. That means that it undergoes both oxidation and reduction when placed in acidified medium, such as dilute sulfuric acid. So this is the ionic equation, but you'll find some books giving you the molecular equation, but the ionic equation is the better one to balance and the better one to write up. So proceeding, we are going to be looking at copper 1 chloride. Now copper 1 chloride, I say that this is a conformation. Copper 1 chloride is one of the reagents that can be used in the laboratory, but I say that most of the compounds of copper are going to be white, of copper under the oxidation state of +1. So copper 1 chloride is a white covalent solid and it's insoluble in water, and it can be prepared simply by boiling a mixture containing copper 2 chloride together with copper tannins present in hydrochloric acid as a medium for the reaction to take place. So what it does is that copper reduces copper 2 chloride to give us copper 1 chloride, and this is what we call a white covalent solid, though it's not commonly said, but you need to know its chemistry. So it does also dissolve in concentrated hydrochloric acid due to the formation of a complex which is going to be dichlorocuprate 1 ion. So the more, if you place hydrochloric acid present in excess here, is that chloride ions are going to be in excess. So more of the chloride ions are going to react with the product that is being formed, which is copper 1 chloride, to give us a complex which is going to be called dichlorocuprate 1 ion. And I've already taught you how to name these complex ions together in the first or the introduction video about transition elements. So just like silver chloride, copper 1 chloride, it is also soluble. Just like silver chloride, also copper 1 chloride is going to be soluble in ammonia solution, forming a complex of diamine copper 1 ion. So the equation is going to be as follows, and they follow the same criteria about balancing them. Now let's go to the main, the common one, which is going to be copper 2 compounds. Now copper, just like I've told you, majority of the transition metal ions are going to exist as hydrated ions in solution due to their small ionic radius and high charge densities. So copper in solution exists as hydrated hexaqua copper 2 ion with this formula, and it's going to be mainly blue majority of its compound in solution are going to be mainly blue, except copper 2 carbonate, which is green in nature, but it's a solid. So looking at for the first compound, you're going to look at how copper 2 oxide is formed, or the chemistry behind it, and we are going to look at first its formation. So we mainly obtain copper 2 oxide after heating copper 2 carbonate. Like we said, copper 2 carbonate is a green solid, but on heating it's going to give us copper oxide, which is always seen as a black solid in the laboratory. So we can also obtain copper 2 oxide simply by heating its hydroxide or its nitrate. When you heat its hydroxide, you're going to get copper 2 oxide together with steam, and when you heat a nitrate, you're going to get copper 2 oxide together with nitrogen dioxide and oxygen gas. So you try writing out majority of both of those equations like I presented one. So copper 2 carbonate, when heated, it gives us copper 2 oxide together with carbon dioxide gas, which, and our requirement here, or our main focus is the copper 2 oxide. Now the chemistry behind it is that it's a basic oxide, and therefore it only reacts with dilute mineral acids or concentrated mineral acids to form the corresponding salts together with water. Like I said, if an oxide reacts with an acid, we always get water, but if an element reacts with an acid, we always get hydrogen gas. So you have to know the difference between the two, and after we form corresponding salts according to the most stable oxidation state. So since +2 is the most stable oxidation state in copper, is what we form. So we form compounds or salts in the +2 oxidation state of copper. Now looking at copper 2 hydroxide, we mainly prepare it under practicals, whereby you get your test solution containing copper 2 ions, and you either add a little of the sodium hydroxide or ammonia solution. And once you do that, is that the copper 2 ions present in the test solution, they react with the hydroxide ions coming from either the ammonia solution or the sodium hydroxide solution, giving you a blue solid or a blue precipitate of copper 2 hydroxide. I hope you have seen this in your laboratory, but when present in excess, always for ammonia we are going to form tetraamine copper 2 ion, a deep blue solution is formed. But for sodium hydroxide, this precipitate persists because there is no complex formation with sodium hydroxide. So looking at its chemistry, we are going to say that copper 2 hydroxide is a basic oxide mainly, and therefore it reacts with dilute acids to form corresponding copper 2 salts together with water. So copper 2 hydroxide reacts with protons to give us copper 2 ions together with water. As we already mentioned, for anything to be basic, always reacts with the acid to give us corresponding salt. Both oxides and hydroxide, they have to give a byproduct of water as another product being formed. Now let's look at the brief chemistry that can be observed under determination of the amount of copper that can be present in impure or blister copper, which is this is the copper that we get after purifying our ore. So let's look at how we can do that on the laboratory basis. Now this question, I presented these notes because some mock bodies are examining it, though it's not common. It's not a common practice to be examined by UNEB. So first, a known mass of impure copper is going to be dissolved in excess concentrated sulfuric acid. And once we do so, we are going to get our resultant solution, and we neutralize it with sodium hydrogen carbonate. Now once we do so, the mixture that we have obtained is going to be reacted with excess potassium iodide, and we do so that we can liberate the iodine, which is present as iodide ions from potassium iodide, according to the following equation. So iodide ions are going to react with the copper ions that are present in the mixture to form copper 1 iodide. Like I've told you, this is one of the confirmatory reagent of confirmatory product to prove that copper is present in the laboratory. And you always get a solution, and then you add excess of potassium iodide. So once you get a white precipitate, this one usually exists as a white precipitate of copper and iodide. That's how you confirm your copper. I hope you know that. So make sure that you review your practical books about this reaction, because it's very, very important. So copper 1 ions react with iodide ions to give us copper 1 iodide together with iodine. So the liberation of iodine is going to make your solution brown. Now you're going to say that the liberated iodine is going to be titrated with a standard solution of sodium thiosulfate using the starch indicator. Remember that we say that in chemical equilibrium, whenever you're having iodine in an experiment, we are always using our standard solution or our standard titrant to be sodium thiosulfate. And whenever you use sodium thiosulfate as a titrant, you are always using starch as an indicator. So proceeding, you're going to say that the concentration of iodine is thus going to be obtained together with the copper 2 ions, and hence the mass of copper present in the mixture is also going to be calculated. So the percentage mass of copper which is going to be present in that mixture is going to be obtained by the following formula. So percentage of copper is going to be given by the mass of copper divided by the mass which you have calculated, divided by the mass of copper present in the impure sample or present in the blister copper. In the blister copper or your impure sample of copper multiplied by 100, and it's going to give you the percentage of copper, and that's how we can obtain the percentage of copper that is present in blister copper in case you come across such a question. And such questions are going to be given marks ranging between 5 to 6 marks, so you need to be very, very attentive when you find them. So proceeding, let's look at some of the qualitative analysis that can be observed under the copper ions that can be present in our test solutions. So when you're going to look at the qualitative analysis as present in the laboratory, when add a solution containing copper 2 ions, we add sodium hydroxide solution. So just like I've already talked about this, is that you're going to get a pale blue precipitate, or simply you can say blue precipitate, which is going to be insoluble in excess. So the equation for that is going to be copper ions reacting the hydroxide ions to give us copper 2 hydroxide, which is going to be our pale blue precipitate. But when you put ammonia solution, the pale blue precipitate is going to dissolve to give a deep blue solution, and this is something that you have been covering ever since your O level. So the observation is pale blue precipitate soluble in excess forming a deep blue solution. And the reason for that is the pale blue precipitate is as a result of formation of copper 2 hydroxide. But this copper 2 hydroxide dissolves in excess ammonia solution to give us a complex of tetraamine copper 2 ion, leaving out the hydroxide ions as a medium present for this complex to be formed. And this formation of this complex, which is tetraamine copper 2 ion, is the one which leads to formation of the deep blue solution. Now looking at the other reagent, which is one of the confirmatory reagents of copper, is going to be the copper iodide solution. Now when you're having the copper iodide solution, that's when you form the other copper 1 iodide, and I've told you it's a white precipitate. Now after forming copper 1 iodide, remember that also these iodide ions are going to be oxidized to iodine. So the white precipitate is due to formation of copper 1 iodide, and then the brown solution is due to formation of iodine. So white precipitate is due to formation of copper 1 iodide, and the brown solution is due to formation of the iodine as an aqueous element. So let's look at the equation. So in the equation, the copper 2 ions react with the iodide ions. So these copper 2 ions are going to oxidize these iodide ions to give us the iodine, which is necessary to convert our solution to be brown. But white precipitates are going to be observed within that brown solution that is being formed. The white precipitates are going to be due to the formation of copper 1 iodide, which is written in this format. So we're going to say that the brown solution turns colorless on addition of sodium thiosulfate, and the reason for that is because sodium thiosulfate reacts with these iodine molecules, forming a complex, and the iodine is going to be reduced to iodide ions. So some textbooks, if at all you add sodium thiosulfate, you need to understand that your brown solution is going to turn colorless, and here if it turns colorless, you'll be remaining with only the white precipitate of copper 1 iodide. So you need to understand that chemistry properly, because this is one of the good confirmatory reagents of copper in the laboratory. And if you're writing this, make sure that you highlight this reagent very well, because it will help you a bunch of issues when you're dealing with your practicals. Now looking at number 4, we are going to look at potassium hexocyanoferrate 2 solution. Now also this is a confirmatory reagent for copper, but here the observation, instead of white precipitate, we see a brown precipitate, which is going to be insoluble in ammonia solution. I'll say that this is also a confirmatory reagent, but if it is set in theory, usually ask you for equations, and that's why it's better for a student to memorize this reagent more as compared to this one. So for this one, it should be for your practical purposes, that whenever you see a step telling you to add potassium hexathionoferrate 2 solution, you need to understand that you are forming a brown precipitate which is going to be insoluble in ammonia solution. So the equation that is going to be formed for that, for those of you who can memorize, is going to be the following, leading to the formation of this brown precipitate, which is in terms of a complex. Now with this, let's cross to zinc, and we also look at the chemistry that is involved in zinc as a transition metal. So looking at zinc, we are going to be starting with this extraction just like we started with copper, and this is the last transition metal that we are covering under the transition elements videos. So this is finalizing all the transition chemistry that we have been covering all along the previous 5 videos. So we are going to look at the extraction of zinc. So just like copper, also zinc has its chief ore from which you extract it mainly on an industrial process, and that is going to be our zinc blende. So it's mainly zinc blende, which can be denoted as zinc sulfide, or some other people use calamine, and calamine is known as zinc carbonate. We are not calling them their chemical names because they are contaminated with other compounds. So that's why zinc carbonate, instead of being called zinc carbonate, is called calamine on an industrial scale. And zinc sulfide, instead of being called zinc sulfide, we are going to call it our zinc blende. And this is the chief ore for extraction of zinc. Now starting with the extraction process of zinc from zinc blende. So this was a typing error. It's not supposed to be iron. So it's supposed to be zinc from zinc blende. So we're going to say that the ore is first concentrated by fourth rotation. And I'll say that mind about the spelling of this word. So by fourth rotation, you have to first give a brief review about what fourth rotation is. So we're going to say that in this method, we get our finely crushed ore and then we mix it with water containing a frothing agent. And once we do so, the mixture is going to be agitated. And we agitate by blowing air through our mixture. And once we do that, is that the froth is going to float to the bottom. And the ore is going to contain, the froth is going to float on the surface of the water or the mixture, and the other impurities are going to be weighted, or they are going to absorb water, and after doing so they sink to the bottom of either the tank or the vessel in which you're trying to carry out your extraction from. And so we are going to get to skim off our froth, and then we extract our ore, we dry it, and then we roast it in air so as we can convert it to zinc oxide. So by doing so, we shall be heating zinc sulfide to get zinc oxide. Now, since our ore is containing other impurities, it also contains galena. Now, galena is the same as little sulfide. So little sulfide also decomposes when you're heating our ore, forming little oxide together with sulfur dioxide as the main impurity that is present in our zinc blende. So zinc sulfide, which is our zinc blende, burns in sufficient oxygen to give us zinc oxide together with sulfur dioxide gas, balancing before the same criteria: metals first, non-metals next, which is sulfur, and then lastly oxygen. So solid sulfide, which is our galena, also reacts with oxygen to give us little oxide together with sulfur dioxide gas. And this is going to give us our other product, which is the main impurity in this ore. So we focus at removing this impurity so that we can remain with zinc oxide, from which we are going to obtain our zinc that is required in this extraction process. So the solid product, the product of roasting, is going to be mixed with limestone together with coke, and is going to be fed into a furnace, and water is going to be blown into this furnace. So what happens is that the coke is going to burn to form carbon dioxide, just like we looked at it in iron. So coke burns in oxygen to give carbon dioxide. But as this carbon dioxide is ascending up the furnace, it's going to meet unburnt coke and they react together, and unburnt coke is going to reduce carbon dioxide for us to obtain carbon monoxide. Now it's this carbon monoxide which is going to reduce our oxides that we got from both zinc blende and Garena, which are zinc oxide together with lead oxide. Both of them are going to be reduced under high temperatures, and zinc oxide is going to be reduced to zinc together with lead oxide to be reduced to lead. But what's going to be separate, or what's going to make them be separable, is that zinc, after being reduced, it is obtained as a gas at the top of the furnace, whereas lead, after being oxidized, it melts and it goes off roast down to the bottom and is tapped off. So zinc is got as a spray, whereas lead moves to the bottom of the furnace, where it's required and terminated or taken off from the furnace because it is not required. So zinc oxide is reduced by carbon monoxide to give you zinc as a gas together with carbon dioxide. But lead, after being reduced by carbon monoxide, we get molten lead together with gaseous carbon dioxide. So proceeding, we're going to say that the zinc is going to leave the furnace as a vapor, which is cooled by a spray of lead. Now for us to get pure zinc, we get pure zinc by cooling it with a spray of lead at the bottom of the furnace, and it's going to solidify on top of the furnace as on top of molten lead. Remember that molten lead is going to be down. It's going to be down. So the more zinc escapes as a vapor, we spray it with lead. So this is going to cause it to melt also, and it's going to come and float on top of lead which has already melted earlier on because it melts fast, and it's going to be tapped off from the top of molten lead, and that's how we are going to obtain our pure zinc, or that's how the extraction of zinc is going to be completed or finished. Now remember that I told you that silica is the main impurity in majority of the ores that are present, because for it exists everywhere, especially where these ores are extracted from. So limestone, which we combine in our mixture, is going to decompose to form calcium oxide together with carbon dioxide. Remember that limestone is the same as calcium carbonate. And once you heat any carbonate, you get an oxide together with carbon dioxide. So the oxide that is being formed reacts with this silica, which is present in our impurity, to form calcium silicate, which is also called slag. So this slag flows off and is tapped off from the bottom, and therefore you have purified your zinc, and by that you are able to retain zinc as a pure metal, pure extracted metal. So let's look at the reactions that can be involved with zinc. So just like any other elements, we say that you have to give conditions together with the products that are being formed. So with air, heated zinc is going to burn to give a blue flame forming zinc oxide. But whenever you're answering a question, you may leave out the color and you just tell us the conditions together with the products that are being formed if you're being asked in theory. So zinc, when heated, reacts with dry oxygen gas to give us zinc oxide. So with water, zinc does not react with cold water, but when it is heated, it reacts with steam. So it only reacts with water in form of steam. So the conditions are heated zinc reacts with steam to give us zinc oxide together with hydrogen gas. And the equation is going to be as follows. So zinc reacts with water to give us zinc oxide together with hydrogen gas. Just like any other metal reacting with any form of water, it gives us an oxide together with hydrogen gas, especially with steam. So looking at reactions with alkalis, you're going to say that zinc reacts with hot concentrated alkalis to form a zincate complex together with hydrogen gas. Now the reason why zinc reacts with alkalis is because zinc as a metal is an amphoteric metal atom, or an amphoteric metal ion in form of ions. So being amphoteric, it reacts with both acids together with alkalis. So zinc reacts with hydroxide ions from either potassium hydroxide or sodium hydroxide or ammonia solution to give us a complex which can either be written in this form, which is called a zincate complex together with hydrogen gas. So you can either give your equation in this format or you can give it in this format. So looking at the reactions with acids, we are going to first look at the reactions with dilute acids. Now zinc, having its stable oxidation state of +2, is going to be able to react with dilute sulfuric acid together with hydrochloric acid, either concentrated or dilute, because we say that hydrochloric acid is a non-oxidizing acid. So it reacts with dilute sulfuric acid together with either concentrated or dilute hydrochloric acid to give us corresponding zinc 2 salts together with hydrogen gas. So the equation is going to be as follows. However, when you use dilute nitric acid, we say that dilute nitric acid, however dilute it is, it still has oxidizing properties. So it oxidizes zinc to zinc 2 nitrate, and the acid, after oxidizing, it gets reduced to ammonium nitrate together with water. So the equation is going to be as follows. Zinc is oxidized to zinc 2 nitrate, and the acid, after oxidizing, is reduced to ammonium nitrate together with water. And this is a redox reaction. You do the redox workout and you see whether you can come up with its balancing, so that you don't have to cram the balancing. So proceeding, let's look at the reactions that are going to be involved with concentrated acids. So concentrated sulfuric acid, being an oxidizing acid, is going to oxidize our zinc to get zinc 2 sulfate together with, after the acid oxidizing, it's going to get reduced, and it's going to get reduced to sulfur dioxide together with water. And the equation is going to be as follows. I say that these are redox reactions, and I've overemphasized about them. I hope you are now well versed with them. So zinc also is also oxidized by hot concentrated nitric acid to give us zinc 2 nitrate, and the acid after that gets reduced to nitrogen dioxide together with water. So zinc is oxidized by hot concentrated nitric acid to give us zinc 2 nitrate, and after the acid oxidizing, it gives us nitrogen dioxide together with water. Now let's look at the reactions of the zinc it has with nonmetals. Now most of these reactions, zinc only reacts with nonmetals when it is heated. So that's a condition that must be quoted before even we start its reactions with metals. So that's why in the general statement I gave, I say that heated zinc is going to react with nonmetals such as nitrogen and dry chlorine gas to form a nitride and a zinc chloride respectively. So the equations are going to be according to the following. So zinc reacts with nitrogen to give zinc nitride, and the balancing is done according to the principles that we already explained of balancing equations. Also, when you heat zinc with chlorine, you're going to get zinc chloride. You can also heat it with dry hydrogen chloride gas. You're going to get zinc chloride together with hydrogen gas. So someone can include it here. So looking at the compounds of zinc, now we are going to say that zinc forms its compounds that are going to be only present in the +2 oxidation state only. So in this state, zinc ion has a fully filled 3d orbital, and therefore, since it has a fully filled 3d orbital or subenergy level, is not going to qualify to show typical transition metal properties because its 3d orbital is fully filled. Which transition metals, to show transition properties, the 3d subenergy level must not be fully filled. So it's not going to be regarded as a typical transition element for the following reasons. One of them is going to be that it's going to have only one oxidation state, which is the +2 oxidation state. Reason being, it leaves a fully filled 3d subenergy level, which is already stable. So it's only going to form one oxidation state, and these compounds are not going to be colored. Reason being, it has a fully filled 3d subenergy level. And lastly, it's not going to be paramagnetic. We say that for a transition metal to be paramagnetic, there must be empty orbitals or unpaired electrons. So since all the 3d subenergy level or 3d orbitals of zinc are fully filled, so that means that it's not going to qualify to be paramagnetic because there are not going to be any unpaired electrons present in those orbitals. So zinc is not paramagnetic, unlike other transition elements. It's also not going to form colored compounds, unlike other transition metal elements. And it's also going to have only one oxidation state, unlike other transition elements. Now let's look at its compounds, and let's start with the zinc oxide. Just like others, we said that we prepare oxides from hydroxides, nitrates together with carbonates. So zinc oxide is a white solid that is going to turn yellow on heating. So that means that it's yellow when warm and it's going to be white on cooling. I hope you know that from the practicals that you have done about chemistry so far. So it can be obtained simply by heating zinc carbonate, and we have said that whenever you heat a carbonate, you get an oxide together with carbon dioxide gas. So I proceed by saying that it's going to be insoluble in water, but it is an amphoteric oxide. Just like I said, zinc is an amphoteric metal together with its compounds. So zinc oxide, zinc hydroxide together with zinc as an element, they are all amphoteric. So therefore, they react with acids together with alkalis. So zinc oxide reacts with dilute acids to form corresponding zinc 2 salt together with water. So zinc oxide reacts with acids, giving us zinc 2 salts together with water, as given by the equation. So proceeding with other reactions, we are going to say that zinc oxide also reacts with hot concentrated alkalis to give us corresponding zincate salts, because being amphoteric, it reacts with alkalis, just like in practicals, to give us the respective complexes. And therefore, we are going to form zincate ions as a complex. I say that you can either opt for this equation or you can opt for this equation. And these equations are mainly handled in practicals, though sometimes we ask them in paper 2 under reagents together with the conditions that are required for those reagents to operate under. Now the other compound you're going to look at is going to be zinc hydroxide. Now we usually prepare zinc hydroxide after getting a water solution and adding either sodium hydroxide or ammonia solution. And it's going to be prepared as you always have it as a white solid. When aqueous sodium hydroxide is being added to a solution containing zinc 2 ions or zinc 2 salt. So zinc 2 ions react with hydroxide ions from the base to give us the zinc 2 hydroxide, and this one exists as our white precipitate. But this precipitate is soluble in both excess sodium hydroxide together with excess ammonia solution, giving a colorless solution if at all they are added in excess. So we're going to say another property of zinc hydroxide is going to be its reaction with dilute acids forming corresponding zinc 2 salts together with water. Now let's dive into the qualitative analysis that can be observed under zinc as an ion in the laboratory. So we're going to first look at its chemistry with sodium hydroxide solution. Now on addition of sodium hydroxide solution, just like we have said that you're going to see a white precipitate of zinc hydroxide, which is soluble in excess due to formation of a complex of the zincate ion, and it's going to result into formation of a colorless solution. So the equations are going to be as follows, as we have already looked at them. So also ammonia solutions, we are going to get a white precipitate which is soluble in excess to form a colorless solution. Now notice that it's only zinc ion that among the amphoteric cations that is only going to dissolve in. So among the ions that form white precipitates as amphoteric cations, it's only zinc that dissolves in ammonia. So ammonia can be its confirmatory reagent. And though it's a preliminary reagent, you cannot use it in practicals to confirm presence of zinc. So the first reaction is going to be the zinc hydroxide, but this zinc hydroxide dissolves in excess to give us a complex of tetramine zinc 2 ion, giving a medium in which that complex is most stable in. Now let's look at another reagent, which is going to be potassium hexacyanoferrate 2 solution, and how it is affected, or how it affects a test solution containing zinc 2 ions. So the observation for that is going to be a white precipitate, which is going to be soluble in aqueous ammonia solution, and the equation is going to be as follows. And this one can also be a confirmatory reagent of the zinc 2 ion in the laboratory. Now the other confirmatory reagent that can confirm zinc, but it's not specifically, is going to be addition of solid ammonium chloride to that test solution, followed by disodium hydrogen phosphate and ammonia solution. And the observation is going to be a white crystalline solid which is going to be soluble in ammonia. Or someone can say white precipitate which is soluble in the ammonia solution. Now this brings us to the end of this video, or to the end of the transition metal elements. Now just like I said, I advise you to share the video to friends. Make sure that you benefit as a group. Let everyone pass chemistry. Do not be selfish. If you're having classmates, make sure that you share the videos to your friends. And to pass highly, make sure that you engage in a lot of discussions as possible. Now a link for our WhatsApp for us to converge students on this platform for you to raise your issues is going to be provided in this video in the description. So make sure that you click into it and you get subscribed straight away to the WhatsApp group that you're going to be using for this channel for concerns and raising issues that can be answered instead of each of you logging my inbox. So I meet in the next video. It has been Olgembe Yusuf, and everything has been presented by Olgembe Yusuf and compiled by Olgembe Yusuf in this channel. So see you in the next video where we are going to be tackling electrochemistry.